Hi, I'm Chris Sensor. Yes, that's my real last name. So today we're going to talk about sign control. I have a table here, all the acronyms that I sometimes use in presentations, so you can translate any alphabet soup that comes out of my mouth. We're going to go through the basics of setting up a swept sign test, and then maybe talk about a little bit of advanced stuff. We're going to go through channel setup, system identification and system verification, then the swept sign test run, and then we'll talk a little bit about notching. I'm pulling up the software here, and we're going to start from scratch. So when you open up Test Lab, and to open up Test Lab, most of us have this link on your desktop. You can also search for sign control in whatever this part of Windows is called. Start menu, I guess. Or if you double click here, that's going to open File Explorer to your Test Lab installation. Here's all the different software products here. And you'll go into Test Lab Environmental and open up Sign Control here. When you do that and Test Lab opens up, you'll hit this little button here, and that'll start a blank project for Sign. And there's a documentation tab here where you can put notes and stuff. Navigator, if you're familiar with Test Lab, this is where you can view results and do a little playing around and calculations and stuff like that. But to set up the test, I almost always just go right to channel setup. And now I'm gonna, have to define a control channel. So channel 1 here is gonna be my control. I'm gonna turn on channel 2 as a measure. Now, the structure that I have on my shaker here is a little cantilever beam. I have input 1 as a control, and you know what? I should have put up a picture, but I do have a picture of it in another presentation, so I can pull that up and show you real quick. I have my shaker. It's a small shaker. There's an armature here, and I've got a test structure on the armature. I have a little control accelerometer here, and I have a measurement accelerometer out at the end of this cantilever, and we're going to measure some pretty cool resonances and stuff when we do that. So that is what the setup looks like. And again, this is going to be channel 1, the control channel, and this is going to be channel 2, right? After that, we put in what other parameters we need, but mostly you want to make sure that your input mode is correct and your actual sensitivity is correct. Now, I'm using two accelerometers that have a nominal 100 millivolt per G sensitivity to them. So I'm just going to use the nominal sensitivity because I'm not doing an actual test on a $1 million satellite. I'm just fooling around here. If you're doing a real test on a real part, make sure you use the actual calibrated values of your accelerometer here. And just for fun, I am going to put in some names here so that we know which accelerometer is which. So we're going to call this control, call this tip, and when we do our test, it's going to show up that way. All right, so we'll go to sign setup, which is the next step here. And we're going to define how our sweep is going to run. I like to start on the top right here, and I'm going to type in beginning frequency of 10 hertz, and I'm going to sweep up to 500 hertz. And I'm going to keep my control estimator as harmonic, and we'll talk about what that means in a couple minutes. Our control strategy is going to be average. There's also extremal control, but again, we'll talk about that later. The main thing here is I'm going to define my sweep rate and my measurement estimators that I'm going to use. So I'm going to select harmonic and peak. And the last bit here is to edit the reference profile. Again, I'm going to go 10 hertz to 500 hertz. And I'm just going to do a 2G sweep here. Pretty straightforward. If you want to have some type of shape to this, you can. A very common question is, how do I set this up so that I have a constant displacement, for example, up to a certain frequency? That's pretty simple. I'll just reset the table here and show that real quick. You can type in your amplitudes in acceleration, velocity, or displacement. So I'll start with a displacement of 0.1 inches, and then I want to go to 20 hertz at 2 Gs, and then all the way up to 500 hertz at 2 Gs, right? And that is going to give me my constant displacement, right? So I'm going to reset this again, and we'll go from 10 again to 500, and we'll just do a 2G sweep here. So flat profile, and now this is all set up. You have the basic stuff ready to run. And the next step is doing system identification. What is system identification? Okay, so we looked at our setup, and now we're going to look at system identification. If you are familiar with modal type tests, very typically they're run open loop, where you just send out a drive signal in volts. You're going to measure the force input into the system, and then you are going to measure the response of your structure with accelerometers, and you'll do acceleration over force measurements. What system identification does is create a transfer function for closed loop control. So what we do first is basically a little modal test, right? We're going to send out an open loop voltage signal and measure what our accelerometer sees. And then we're able to calculate the system transfer function in Gs per volt. So the drive signal goes out in volts, the measurement comes back in Gs, and we have a system transfer function in Gs per volt. And that gives us an idea of what our drive voltage needs to be to achieve our test level in Gs. What you do to get there is create this system transfer function and invert it. So again, this is a picture of a real test here. Well, real-ish, at least. We've got our control accelerometer, and we've got our drive output to our shaker amplifier. We output that drive to the shaker, we measure what the accelerometer is reading, and then we calculate this function. Then we calculate the inverse transfer function. So we have our system transfer function, which is output over input in Gs per volt. Then we calculate this inverse transfer function, and you end up with something in volts per G. And then you can take this signal in volts per G and multiply it by your reference spectrum. The G's cancel out, and then you end up with your initial drive voltage spectrum for control. Coherence is another thing that we measure in system identification. It's an indicator of how good the system transfer function is. And for sine especially, you want to have really high coherence between your drive and your measurement. And if you don't, you might have picked a control location that is not the best control location for your test. So the last thing is to talk about the actual procedure for system identification. Then we're going to go in and run system identification, and we will see what our predicted drive voltage is going to be. So the process for system identification is when you hit start, it arms the system and then measures the background noise without any excitation. That background noise is a very important measurement. We'll talk about that when we do it. Then we start to build up the drive voltage until we reach a minimum drive level. And then we start to take samples and average them together. And we end up with a result that is our system transfer function. And then we extrapolate these results into test levels and report them out in system verification. System verification is a tool, and we'll take a look at this, to display the pre-test data. So we'll have all the system identification results and a forward prediction of the drive and response channels. So now let's take a look at that in the software. Okay, so we've set up our sign test here. This looks weird again because it's in inches now, but if we go back to our regular display, we have a flat G sweep. And we'll go to system identification and we're going to hit start. Now this is going to send out a signal after we measure some noise. So what this initializing is doing is telling the front end what we're doing. And then there's some settling where we're going to measure the noise. And now we're going to start to build up our drive voltage. Now, you might look at this and go, geez, it's taken really long to take an average. And it is. So here's a little trick. The problem here is our system identification is doing broadband random excitation because that's a very safe way to excite a structure. Sign is a very dangerous way to excite a structure because you're pouring all your energy into one frequency line. With random excitation, it's much gentler. You're pouring your energy across a frequency spectrum. But what we're trying to do here is match the frequency resolution of our sine sweep. Sine sweeps have very fine resolution. And if you have very fine resolution, that means that it takes a longer time to take a random block, right? It's an inverse relationship. So if I have a frequency resolution of 1 Hertz, I have to sample for 1 second before I can calculate a PSD. If I have a frequency resolution of 4 Hertz, I only have to take a time sample of a 1/4 second to calculate a PSD. So because the system identification is trying to match the sign setup, we'll show you in just a second here. If I look at my system identification settings, we're saving some data here, background, there we go. I'm trying to match these settings from the sign setup, so I have a frequency resolution of 0.19 Hertz. And if you calculate that, that's a little bit less than 8 seconds that we have to sample to take one FFT measurement. Sometimes, and again, this is highly dependent on the test article and what you're trying to accomplish, and what you're trying to accomplish specifically with system identification. If you're using this for notching, and we'll touch on that later, then having a fine frequency resolution and spending the extra time is fine. If you just want to get a faster result, you can uncheck this box. Again, this is system identification settings. And if you uncheck the from setup box, you can change this frequency resolution to something that is maybe a little faster for you. So a lot of times I'll come in here and I'll change this to 0.78. And we'll see here that system identification will be just that much faster. So we've got our buildup, measured our noise, and now we're starting to take data. And we'll see these blocks are captured a lot faster. So this is an option for you to speed up the pretest. Again, depending on what you're trying to do, it may or may not be appropriate, but it is an option for you. So we'll just use this last pretest, and you can see acquisition tells you what our background noise measurements are. It tells you what our signal to noise ratio is, which is very good for this test. And we get our RMS measurements from the excitation. So you can see I am having a relatively gentle excitation versus my actual sign test. And these predicted values also show up here in system verification. So here's the summary. This is the same table as before. I have some data up here I can display. This is the system transfer function, system FRF. And I can see my coherence versus output 1 is very good. It's almost 1 across the board. If you come in here, sometimes this is set to free, and then it looks like you have terrible coherence, right? But always look at this scale. I'm basically going from 1 to 1. So if I reset this, coherence again is a value between 0 and 1, and this is telling us how good our measurement setup is, the quality of our transfer function. But if I set this to something reasonable, like 0 to 1.1, so I can see the trace, now I can see that there really isn't much variation at all in my coherence. Down here, I can get some other information like what my ranging is set to, and I might have a suggested range that I want to reset to. I'm just going to leave these alone. Then I have my open loop threshold. Sometimes these values are too high. For instance, if you're running a 1G sine sweep and you have a 100 millivolt per G accelerometer, this threshold might be 0.5 Gs. And that's going to throw an open loop at you when you go to run the test. So you might have to adjust these open loop threshold settings, depending on the test that you're going to do. We're doing a 2G sweep, and we have a threshold here of 0.05 Gs, so this is appropriate for my test. The next thing is, if we go to summary, this gives me a predicted drive peak level in sine, but I can also go to drives here, and this is my drive spectrum in volts that my controller is going to output. Now, if you look at this, you'll notice, boy, that's awful similar to that system transfer function. And in fact, that's because we invert this system transfer function again and multiply it by the reference spectrum to get this. So it's basically going to look like the inverse of your system transfer function, the shape of it. The last thing I can do is look at my predicted responses. So I'll go over here to responses, and then I'll select both of these, and I can see my control, and I can see the peaks in my response at the end of my cantilever. If I go here and I'm gonna right click on my cursor, I'm gonna move to my global maximum. I can see my frequency is at 36.6 Hertz. So when we do the sweep, we'll see exactly what this frequency is, and we can see the difference between the accuracy of sine versus the accuracy of random. Our next step from here is to go into sine control and run the test. But before we do that, let's take a look at some of these things we kind of glossed over when we were doing the sine setup, namely the control estimators. And this is a very, very, very important thing to understand with sine testing in particular. So again, we're going to go into our swept sine information here. There's two basic sine tests that you run. There's swept sine, and that's what we're talking about today. And then there's sine dwell, which is a topic for another day. But the basic idea behind swept sine is we're going to have a single amplitude at any one point in time. And as a basic requirement, we need in a test specification the amplitude and frequency breakpoints that we program in to our test definition. We need to know the duration of the test, i.e., are we going to do one sweep? Are we going to do 10 sweeps? Are we going to sweep for an hour? Are we going to sweep for 30 seconds or a certain number of cycles? That duration has to be specified, and as a basic requirement of a specification, you also need to put in a sweep speed, i.e., how fast am I going to change my frequency? This can be in octaves per minute or in a linear sense in hertz per minute. Sine dwell, again, we're not going to talk about today, but that's basically a test where you run at a single frequency over a period of time or number of cycles. With sine testing versus a random test or other test types, you have some advantages here. And one of the advantages is you have very simple control and very good signal to noise. You get a very precise determination of your eigenfrequencies, e.g. your references you're going to use. And you have the ability to determine the effects of harmonics on a test structure. Because you're exciting one frequency at a time, you can see the effect of the harmonics of that excitation. So you're exciting at 50 hertz, you may also see the effects at 100 hertz, 150 hertz, 200 hertz, etc. And sine testing is ideal for substructures that are going to be mounted on a parent structure. For example, a turbocharger on an engine is going to be driven by the rotational speed of the engine, which is essentially a sine sweep. Sine is a potentially longer test than other test types. You have a very high potential for overtesting because you're pouring all your energy in at a single frequency. So when you hit a resonance, you really hit a resonance. You have structures with complicated geometry, and you might not expose eigenfrequencies with a sine sweep that you would with random that's exciting a whole frequency band. So that's a disadvantage there. Our sine control loop is pretty straightforward to understand. We have our accelerometer, we measure a response, we decide whether we're in our control specifications or not. Then we calculate this updated inverse transfer function, estimate what our next drive amplitude needs to be in volts. We check our notches, and then we move to the next frequency. In the time it took me to explain this, the controller will have completed several hundred control loops. So this is happening very fast. And how fast the controller corrects for amplitude can be controlled with something called compression factor, and we'll get to that in a minute. But here's a little quiz for everybody. I have a sine wave here. I have my tick marks at -5 and 5 volts. What is the amplitude of this sine wave? Who says 5 volts? Anyone out there? What about 10 volts? And 3.5 volts? All of those answers are correct. They just have different scaling nomenclature to it. We have a 5-volt peak amplitude, we have a 3.5-volt RMS amplitude, and we have a 10-volt peak-to-peak amplitude. So it's very important to understand the amplitude scaling when somebody hands you a test spec and says, do a 5G sine sweep. Well, that doesn't really answer my question, right? Do I mean 5G's peak, 5G's peak to peak, 5G's RMS? You can imagine, depending on what the answer is to that, that I'm actually going to have very different excitation levels for my test. That complicates sine, right? What is my amplitude? Now, we might think, okay, so let's take an FFT and decide what the amplitude is from the FFT. There's a problem with that. Sine sweeps are fast, but FFT processing, by the very math that gets us there, is slow, right? You need to take a sample that's at least as long as the inverse of the frequency resolution that you want in your result. Furthermore, how the FFT is processed with sine, because the excitation frequency is constantly changing, can lead to inconsistent results depending on the settings. And if you believe it, all three of these plots, even though they look widely different, are from the same source sine signal processed into FFTs in different ways, different overlap factors, different windows, et cetera, et cetera. So the results of the FFT for sine can be misleading. The best and fastest thing to do is just pull your amplitude directly from your time domain data. Well, there's an additional complication here that you run into. In a perfect sine wave, your peak, peak to peak, and RMS are all related to each other mathematically. However, in the real world, we have this kind of scenario. My controller is going to send out this voltage signal to the shaker. What my accelerometer is going to measure is this red noise stuff. It has all the harmonics of the structure. If there's any rattling or impacting that happens, you get all this noise that's feeding into the control accelerometer from different frequencies. And typically what we want for sine is to understand what's happening at the exact frequency of excitation. In order to do that, we have a couple different ways of measuring amplitude. There's a harmonic, also known as a tracking filter. And what this does, well, I have a slide on this next. So for now, we'll just say you have a harmonic, RMS, average, and peak estimators. How do these work? Okay, so the harmonic estimator takes your noisy sine signal, puts a tracking filter, which is essentially a band pass filter that's centered at the excitation frequency, right? We're generating the signal, so we know exactly what the excitation frequency is at any point in time. And we center this band pass filter at the excitation frequency. And what that does is it suppresses all the harmonics and turns this noisy signal into a nice clean sine wave. And then we can pull the amplitude directly from this filtered data. Okay? But what if I am concerned about the noise? Well, then you have these other three estimators that are going to take the noise into account. We have our RMS estimator, which is the next most conservative way, i.e., if you use an RMS estimator over harmonic, your drive voltage is going to be lower because the RMS estimator, which is the black trace here, reads higher. So the control is going to reduce the amplitude, the drive amplitude at this point, to get closer to our reference. Next, we have our average, which again, versus harmonic, you're going to see more deviation. So average is going to be even a little more conservative, i.e., this drive voltage for using the average estimator as control is going to be even lower than harmonic and RMS. And then our last estimator is peak. And overall, peak just looks at one block of sine data and pulls the highest absolute value amplitude out and uses that for control. Peak is going to be the most conservative estimation method. As you can see here, it's reading higher than harmonic at almost all frequencies. And so you're going to get the most conservative test out of peak. There's a caveat here to using RMS, peak, or average, and that is you can't get phase information. You look at this schlocky wave here, and you'd have a lot of variation in phase because of the harmonics, as opposed to this nice, clean sine signal. You get a very good estimation of phase from the harmonic filter. So harmonic gives you phase, RMS, average, and peak do not. Thankfully, we can turn them all on in the software. Let's take a look at what happens here. And now, to make this more complicated for me, my setup, in addition to what I have in this picture, you can see this little hole here. I've put a bolt in that hole, and it's a loose bolt. So I'm going to see a lot of rattling. If I didn't have that in there, my peak and harmonic estimator is going to be almost identical throughout the test. But we're going to run this test now, and we're going to see what that looks like. So again, I have my control strategy set to average and my control estimator set to harmonic. This control strategy doesn't really matter right now because I'm only using one control accelerometer. I'm going to turn on RMS and average in the measurement so we can compare these results. So again, system verification, I'm going to just make sure we're all set here, and then we can go into sign control. I'm going to hit ARM, and I am going to pull in my other data. So to do that, I'm going to open Data Explorer here. I'm going to go into Online Data, Sweep, and I'm going to go into Harmonic Spectrum, and I'm going to pull out my tip harmonic in here. So average control is going to match my harmonic spectrum for control. So I'm not going to bother having two traces there. But now I'm also going to put in the peak spectra as well, so we can look at that. So I'll pull in the control and tip peak spectra. So now I'm ready to go. I'm going to hit start, and we're going to have some startup here. And this is our average control. And again, peak versus average control. There's a little jitter on startup because of my rattling bolt. As we get higher in frequency, the displacement is going to decrease, so we won't see as much. Yeah. All right. We can see how the response at our tip location also affects our control. And you can see a lot of difference here between peak, which is in cyan, and the harmonic estimator, which is in blue. If you have a component and you're really concerned about overtest, then maybe using peak estimator for control is a good idea. Or you might even consider using peak as a notching channel. And we'll talk about that in just a second. So that's my initial sign sweep. Right, there's a couple other things to keep in mind about doing sign sweeps. You have two parameters here. Right, the compression factor. Compression factor can affect how fast the control works. And sometimes you might think, oh, well, don't I always want the fastest reaction? Well, not in all cases. So you can see what happens in this test with a compression factor of 1. I basically start to overcorrect, and I'm correcting faster than my system responds. So I have an unstable control that way. Same thing with setting your compression factor too high. A higher compression factor slows down your control. And in this case, my compression factor of 20, it just didn't correct basically at all until I just hit an abort limit. So you have to optimize that compression factor. Typically a value between 3 and 4 is appropriate, but sometimes you need to change that. And that's right here. So we're running at a compression factor of 4. If I change to a compression factor of 1, I'm just going to call this CF1. Okay. We'll hit run here. When we go through this resonance, we might get some instability. There's our resonance again. So if we look at this from our previous test, we can see that the compression factor being faster is actually helping us here. This is our previous test that we just run with a compression factor of 4. Compression factor of 1 seems to be helping us here. But you can also see, if we look in here, right, you see up at this higher frequency, our oscillation in our control is a lot more, whereas the other test was smoother, and sometimes that can be undesirable. Right? Especially for fast sine sweeps, you get this oscillation here coming off the resonance that can be undesirable. So a slower compression factor can smooth that out in the response. Right? So we see down here at the lower frequencies, the lower compression factor helped us. At the higher frequencies, it didn't help us as much. And in fact, one might argue in here that this was too much jitter and control. We want that control to maybe be smoother. Right? We can go back and do the opposite thing, set a compression factor real high to the highest level. And now we can see that we have a really slow control here. We're not correcting that as fast and bringing it back down to the reference. So again, a compression factor that's too high or too low for a particular test might be undesirable. You might also be thinking to yourself, well, what if I have a test where I want a faster compression factor at lower frequencies and a higher compression factor at the higher frequencies? Well, that's pretty straightforward. You can actually do this tabulated setup where you have tabulated compression factor, so I can have my compression factor low here, and maybe by 60 hertz, I'm gonna have it at 4. Something like that. And then that way you can have different compression factors throughout the test if you want. So we'll set this back down and let's talk a little bit about notching. Notching is a way to reduce vibration at a response accelerometer. It's called notching because it puts a notch in the profile there. One of the applications for this is force limiting, which is done in satellite testing a lot. We have a whole bunch of force cells, and you want to control how much force goes in because, again, we have different mechanical impedance between our field condition and our lab condition. In the lab, on a shaker table, it's always going to be much stiffer boundary conditions than out in the field. So we have this mismatch, and we can limit on force, we can limit on strain, and be able to even do derived channels to limit on moments or on overall force input to the structure based on a number of force gauges. If we go back into the software, we can take a look at what happens when we put a notch in. So to create a notch, go into Sign Setup, I'm going to define a notch profile, and I'm going to hit Create here, and we're going to go from 20 to, let's say, 50 Hertz, and we're going to limit at 20 Gs. All right. So now I'm just going to apply that to our measurement channel. I'll go back to channel safety parameters and apply this 20G limit to the notch profile. And now if I go back to system verification, I have an interesting new tool here. If I go to pretest analysis, it'll show me the results of my notch. So here's the peak it's estimating, and here is the notched channel. So that is what my notch is going to look like. So let's go ahead and run that test with a notch. And again, what that's doing is reducing the overall vibration level at the response location. And there's going to be a corresponding dip in my control there as well. Let's take a look at what happens. Here we go. Uh-oh. We have a little bit of overshoot there, don't we? So sometimes this is undesirable, and there's actually a tool that we have that's kind of fun to play with and dead useful, is what we can do is pre-notch. The software doesn't know we have to notch until we exceed the notch limit. But a lot of times that overshoot is no good. What we can do is come in here and we can load the data from a previous system identification. Okay. So we can see our notch here, and what we can do is pre-notch the drive, and I'm going to change my actual profile. All right, so now my reference profile is a little different because I've incorporated this notch right into it, into the control. And that's the basics of running swept sine and doing notching. Thanks, everyone.